So in the recent years, we have seen a lot of different CPUs coming out, like the Ryzen 5, Ryzen 7, Ryzen 9, and even the AMD's Threadripper. So a normal question comes that will this trend of faster CPUs continue indefinitely in the future, or is there a stop to this upward trend? So in 1975, Gordon Moore, the co-founder of Intel, predicted a rule which said that in every 2 years computing power doubles. So this was just a rule, not a law, and Gordon Moore figured this rule by just evaluating and analyzing the different computing data at that time, but it was marketed as a law and the name Moore's Law. I guess this was just to tell the world about the supremacy of Intel in the chip market. But let's first understand what do we mean by computing power. So whenever we are comparing two computers and we say that this computer is more powerful than that computer, we are simply referring to its CPUs, GPUs, RAM or hard disk. But all these components are made up of silicon chips, silicon wafers, silicon semiconductors. So if we are comparing two CPUs and we say this one is faster than that one, we are simply referring to the fact that the powerful CPU can do the same calculation in a small amount of time. So the faster CPU simply has a lot of different components inside it as compared to the less powerful CPU. So a CPU has transistors, different components like the nodes, gateways, channels. So if the number of transistors or channels increases, the power of the CPU also increases. But the thing is, if you increase the number of transistors in a chip, then you have to reduce the size of individual transistors or individual component. So take a look at this graph. In 1972, Intel 4000 series had just 2000 transistors in the chip. But in 2019, Ryzen 7 had about 5 billion transistors. So that is a difference of 2.5 million. So the next question comes that will this trend of ever increasing transistors continue in the future? Will we see a processor with 20 billion transistors or even 50 billion transistors? So if we have to see those types of chips, the size of individual transistors need to get a lot smaller. So let us understand it with an example. So whenever you are purchasing smartphones or a laptop, you must have come across the section of the CPU where it says manufacturing process 14 nanometers or 12 nanometers or 8 nanometers. So that number in simple terms is referring to the size of the transistor. So if a CPU or a processor is built by an 8 nanometer process, it simply means that the transistor size is just 8 nanometers. So if we want more powerful CPUs, we need to reduce this number maybe to 5 nanometers, to 2 nanometers, 1 nanometer or even 0.5 nanometers. So the problem comes when we reach the limit of 1 nanometer. So let's understand this fact by first understanding what a silicon wafer is. So a silicon wafer is made up of silicon atoms, and on that silicon wafer the transistors are embedded by a technique known as photolithography. So we don't need to get in detail with that technique, but the simple thing is that those silicon wafers are built up of silicon atoms, and each silicon atom is just 0.2 nanometers across. So if you are having a transistor which is just 8 nanometers across, then in effect you are just computing on 40 silicon atoms. So when you reach the limit of 1 nanometers, you are in effect computing on just 5 silicon atoms, and at that limit the problems arises. So the first problem is of thermodynamics. So the first problem says that the heat produced by those transistors will be so much that it can easily melt the CPU itself. In order to understand this problem, let's take this example. So let's say we assign a task A to those 40 atoms which were in the 8 nanometer chip. So those atoms need to perform a task B, but now we assign that same task to those 5 atoms, and now they have to perform the same task B. But those 5 atoms need to work a lot harder to give us the same result. So in that process, these 5 atoms produce so much heat that they can melt the CPU itself. The second problem comes from quantum mechanics. So if you have attended first level college physics, then you must have heard the term quantum tunneling. If not, then I'll try my best to help you understand it in simple terms. So let's take an example of a wire carrying electric current. So electricity is conducted by electrons moving across the wire. So in normal circumstances, we don't expect the electrons to jump out of the boundary of the wire and sit on the other side. They can only travel along the wire. But quantum mechanics says that under certain conditions, it is possible for the electrons to jump out of the wire and get leaked. So when you are computing across 5 atoms, the electrons gets leaked. The electrons get leaked from the wire that are present in the silicon wafer, and that breaks the computing of the CPU or the chip. So when will this limit be reached? In 1 decade. In 1 decade, the Moore's law is going to end and the limit of 1 nanometer will be reached. So does this mean that after a decade there will be no advancement in computing speeds? Then no. It simply means that after a decade we need to shift to some different types of chips, different types of conductors. So some of the contenders are a solid 3-dimensional chip as compared to the 2-dimensional chip that we currently use in every device. And there are some exotic ones like biological chips or molecular chips or DNA chips. But these are so exotic that we don't need to concern ourselves with those chips. But in a decade we can see the Moore's law getting to an end. So that was it, guys. I hope this video was informative. I tried to keep this video as non-technical as possibly I can, but if you think that some parts of this video were a lot technical and you were not able to understand, then please let me know in the comments below and I'll try my best to use more simpler words to help you understand. So that was it, guys, and subscribe so that you can get these videos the moment they are released. Thanks for watching and I'll see you soon.